Wiring 3 L6-30R outlets in a delta configuration to the XYZ phases of the L21-30R will provide 208 volts 3-phase power to the L6-30R outlets. Each L6-30R outlet can provide 30 amps at 208 volts, allowing you to draw a total of 24 amps generated from all three phases. However, this configuration isn't recommended or industry standard for powering single-phase equipment from a three-phase power source. The primary concern involves the absence of isolation between the three phases. If one L6-30R outlet overloads or short circuits, it could trigger a ground fault affecting the entire system. For safety and proper function, using an isolation transformer or a three-phase power distribution unit (PDU) with built-in phase isolation is advised. The reason PLC engineering may not offer L21-30 to L6-30 PDU likely stems from these safety concerns, ensuring product safety and adherence to industry standards. Let's examine alternative solutions for powering single-phase equipment from a three-phase source. Firstly, utilize an isolation transformer. An isolation transformer provides isolation between the primary and secondary windings. This prevents ground faults from spreading from the three-phase power source to the single-phase equipment. Secondly, employ a three-phase PDU with built-in isolation. These PDU integrate isolation transformers to isolate the three phases. Thirdly, consider a wye-delta transformer. A wye-delta transformer converts three-phase power from a Y configuration to a delta configuration, isolating the phases. These options offer enhanced safety and reliability compared to the delta wiring configuration, although they are more costly. Let's delve deeper into the technical aspects and safety considerations. When dealing with electrical systems, understanding the implications of different wiring configurations is critical. The delta configuration, while seemingly straightforward, introduces complexities concerning safety and isolation. In a delta configuration without isolation, a fault in one phase can easily propagate to other phases, potentially causing widespread damage and posing a significant safety hazard. The absence of a neutral connection in a delta system also means that there's no direct path for fault current to return to the source, which can delay the activation of overcurrent protection devices like circuit breakers. Isolation transformers address this issue by creating a separate electrical circuit, physically isolating the primary and secondary windings. This isolation prevents the flow of fault current between the input and output sides, limiting the impact of a fault to the isolated circuit. The use of a three-phase PDU with built-in isolation offers a more integrated solution. These PDU are specifically designed to provide safe and reliable power distribution in environments where multiple devices need to be powered from a three-phase source. They typically include features like overcurrent protection, surge suppression, and voltage regulation, in addition to the isolation transformer. Wye-delta transformers provide another layer of isolation by converting the three-phase power from a Y configuration, which has a neutral connection, to a delta configuration, which does not. This conversion not only provides isolation, but also allows for voltage adjustments to better match the requirements of the connected equipment. When selecting an appropriate solution, it's important to consider the specific requirements of the equipment being powered, the available power source, and the overall safety requirements of the installation. A thorough understanding of these factors will help ensure that the chosen solution provides reliable and safe power distribution. Now, let's explore the relevant sections of the National Electrical Code, NEC 2014 edition, to further understand the safety and installation requirements for these types of systems. While the NEC doesn't specifically prohibit the delta wiring configuration, it does emphasize the importance of providing adequate overcurrent protection and ground fault protection for all electrical systems. Article 210.8 Ground Fault Circuit Interrupter Protection for Personnel outlines the requirements for ground fault circuit interrupter (GFCI) protection in various locations, including those where equipment is likely to be used by personnel. While this article primarily focuses on single-phase systems, the principles of ground fault protection are equally applicable to three-phase systems. Article 250 Grounding and Bonding provides detailed requirements for grounding and bonding electrical systems to ensure electrical safety. Section 250.20 System Grounding specifies the conditions under which electrical systems are required to be grounded. In the case of a delta-connected system, grounding may not be required, but it's often recommended to improve system stability and provide a path for fault current to return to the source. Section 250.24 Grounding Service Applied Alternating Current Systems provides requirements for grounding separately derived systems, such as those supplied by isolation transformers. These requirements are designed to ensure that the grounding system is properly installed and maintained to minimize the risk of electrical shock and fire. Article 450 Transformers provides requirements for the installation and protection of transformers, including isolation transformers and wye-delta transformers. Section 450.3 Overcurrent Protection specifies the requirements for overcurrent protection of transformers, including the sizing of fuses and circuit breakers. Section 450.11 Guarding provides requirements for guarding transformers to prevent accidental contact with energized pots. It's also crucial to consult with a qualified electrician to ensure that the chosen wiring configuration and protection devices comply with all applicable codes and standards. A qualified electrician can assess the specific requirements of the installation and provide expert guidance on selecting and installing the appropriate equipment. Additionally, regular inspection and maintenance of the electrical system are essential to ensure its continued safety and reliability. This includes checking for loose connections, damaged insulation, and other potential hazards. By following these guidelines and consulting with qualified professionals, you can ensure that your electrical system is safe, reliable, and compliant with all applicable codes and standards. Furthermore, understanding the concept of apparent power, real power, and reactive power is essential when dealing with power supplies that have active power factor correction (APFC). Apparent power, measured in volt-amps, represents the total power supplied to a circuit, including both real power and reactive power. Real power, measured in watts, W, is the actual power consumed by the load and performs useful work. Reactive power, measured in volt-amps, reactive, VAR, is the power that oscillates between the source and the load and does not perform useful work. Power factor, PF, is the ratio of real power to apparent power and indicates how effectively the electrical power is being used. A power factor of 1 indicates that all the power supplied is being used effectively, while a power factor less than 1 indicates that some of the power is being wasted as reactive power. APFC power supplies are designed to improve the power factor of the load, reducing the amount of reactive power and increasing the amount of real power. This can lead to several benefits, including reduced energy consumption, lower utility bills, and improved system performance. However, it's important to note that even with APFC, power supplies still draw some reactive power, and this needs to be taken into account when sizing the power distribution system. When calculating the total power demand of the equipment, it's important to use the apparent power, VAR, rating of the power supplies rather than the real power, W, rating. This will ensure that the power distribution system is adequately sized to handle the total power demand, including both real power and reactive power. Additionally, it's important to consider the inrush current of the power supplies. Inrush current is the high, instantaneous current drawn by a power supply when it is first turned on. This current can be several times higher than the normal operating current and can cause voltage dips and other problems if the power distribution system is not adequately sized. To mitigate the effects of inrush current, it's often necessary to use soft-start circuits or other current-limiting devices. These devices gradually increase the current drawn by the power supply, reducing the peak inrush current and preventing voltage dips. In summary, when dealing with power supplies that have APFC, it's important to understand the concepts of apparent power, real power, and reactive power. Use the apparent power rating of the power supplies to calculate the total power demand and consider the inrush current when sizing the power distribution system. By following these guidelines, you can ensure that the power distribution system is adequately sized to handle the power demand of the equipment and that the system operates safely and reliably. Let's look into grounding and bonding considerations to emphasize safety. Grounding and bonding are essential for electrical safety, providing a low impedance path for fault current to return to the source, minimizing the risk of electric shock and fire. Grounding refers to the connection of the electrical system to the earth, while bonding refers to the connection of non-current carrying metal parts to create an electrically conductive path. In a three-phase system, grounding can be achieved by connecting the neutral point of the Y-connected transformer to the earth. This provides a reference point for the voltage and helps to stabilize the system. Bonding is used to connect all non-current carrying metal parts such as equipment enclosures, conduit, and cable trays to create a continuous electrical path. This path allows fault current to flow back to the source, tripping the overcurrent protection device and de-energizing the circuit. It's important to ensure that the grounding and bonding system is properly installed and maintained to provide effective protection against electrical hazards. This includes using the correct size conductors, making secure connections, and regularly inspecting the system for damage or corrosion. The NEC provides detailed requirements for grounding and bonding in Article 250. This article specifies the types of grounding and bonding conductors that are permitted, the methods for making connections, and the requirements for grounding electrodes. In addition to the NEC requirements, it's also important to follow industry best practices for grounding and bonding. This includes using a dedicated grounding conductor for each circuit, avoiding ground loops, and minimizing the length of grounding conductors. Ground loops occur when there are multiple paths for ground current to flow, which can cause noise and interference in the electrical system. To avoid ground loops, it's important to ensure that there is only one path for ground current to return to the source. Minimizing the length of grounding conductors helps to reduce the impedance of the grounding path, which improves the effectiveness of the grounding system. This can be achieved by locating the grounding electrode as close as possible to the equipment being grounded and by using short, direct grounding conductors. In summary, grounding and bonding are essential for electrical safety, providing a low impedance path for fault current to return to the source. Follow the requirements of the NEC and industry best practices to ensure that the grounding and bonding system is properly installed and maintained. Regular inspection and maintenance of the grounding and bonding system are also important to ensure its continued effectiveness. Let's discuss overload and short-circuit protection. Overload and short-circuit protection are essential for preventing damage to electrical equipment and ensuring the safety of personnel. Overload protection is designed to protect against excessive current flow that is above the normal operating current of the equipment, but not high enough to cause an immediate short circuit. Short-circuit protection is designed to protect against very high current flow that occurs when there is a direct short between two conductors. Overload protection is typically provided by circuit breakers or fuses that are sized to protect the equipment from overheating. These devices are designed to trip or blow when the current exceeds a certain level for a specified period of time. Short-circuit protection is also provided by circuit breakers or fuses, but these devices are designed to trip or blow very quickly in response to a high current flow. The NEC provides detailed requirements for overload and short-circuit protection in Article 240. This article specifies the types of overcurrent protection devices that are permitted, the methods for sizing these devices, and the requirements for their installation. When selecting overcurrent protection devices, it's important to consider the characteristics of the equipment being protected. This includes the normal operating current, the inrush current, and the thermal withstand capability. The overcurrent protection device should be sized to protect the equipment from overheating without causing nuisance tripping during normal operation. It's also important to consider the interrupting rating of the overcurrent protection device. The interrupting rating is the maximum fault current that the device can safely interrupt without being damaged. The interrupting rating should be high enough to handle the maximum fault current that is likely to occur in the circuit. In addition to the NEC requirements, it's also important to follow industry best practices for overload and short-circuit protection. This includes using appropriately sized conductors, avoiding undersized or overloaded circuits, and regularly inspecting the overcurrent protection devices for damage or wear. Undersized conductors can overheat and cause a fire hazard, while overloaded circuits can cause the overcurrent protection devices to trip frequently. Regular inspection of the overcurrent protection devices can help to identify any potential problems before they lead to a failure. In summary, overload and short-circuit protection are essential for preventing damage to electrical equipment and ensuring the safety of personnel. Follow the requirements of the NEC and industry best practices to ensure that the overcurrent protection devices are properly sized, installed, and maintained. Regular inspection and maintenance of the electrical system are also important to ensure its continued safety and reliability. It's also good to explore power distribution units (PDUs). Power distribution units (PDUs) are used to distribute electrical power to multiple devices from a single power source. They are commonly used in data centers, server rooms, and other environments where multiple devices need to be powered. PDU are available in a variety of configurations, including rack-mounted, floor-mounted, and wall-mounted. They can also be configured with different types of outlets, such as 5-15R, 5-20R, L5-30R, L6-30R, and C13/C19 outlets. When selecting a PDU, it's important to consider the power requirements of the devices that will be connected to it. This includes the voltage, current, and power factor. The PDU should be sized to handle the total power demand of the connected devices, with some margin for future growth. It's also important to consider the features of the PDU, such as overcurrent protection, surge suppression, and remote monitoring. Overcurrent protection is essential for preventing damage to the PDU and the connected devices in the event of an overload or short circuit. Surge suppression protects the PDU and the connected devices from voltage spikes and surges. Remote monitoring allows you to monitor the power consumption of the PDU and the connected devices from a remote location. This can be helpful for identifying potential problems and optimizing power usage. In addition to these features, some PDU also include advanced features such as automatic transfer switching (ATS) and power factor correction (PFC). ATS allows the PDU to automatically switch to a backup power source in the event of a power outage. PFC improves the power factor of the load, reducing the amount of reactive power and improving the efficiency of the electrical system. When installing a PDU, it's important to follow the manufacturer's instructions and all applicable electrical codes. This includes properly grounding the PDU, using appropriately sized conductors, and providing adequate ventilation. It's also important to regularly inspect the PDU for damage or wear. This includes checking the outlets for loose connections, the power cord for damage, and the overcurrent protection devices for proper operation. In summary, PDU are used to distribute electrical power to multiple devices from a single power source. When selecting a PDU, it's important to consider the power requirements of the connected devices, the features of the PDU, and the installation requirements. Regular inspection and maintenance of the PDU are also important to ensure its continued safety and reliability.